Good morning, everyone. Today is May 12th, 2018. And this is the John Chappell Natural Philosophy Society Science Chat. And this is sponsored by the John Chappell Natural Philosophy Society. And you can find our website at naturalphilosophy.org, where you can join us. We discuss all kinds of things in our forums. And you can also check us out on Facebook. And we have lots of YouTube videos. We archive these science chats on YouTube. And we have an upcoming conference coming up, June 27th to the 30th. So that is coming right up about a month and a half from now at the campus of the University of Connecticut. So I've signed up. I've got my airline ticket. I've got my hotel room booked. Bill Lucas is also coming, and he's actually going to be staying with me in my hotel room. The hotel rooms can hold up to 3 people in their economy dorms. And so I could take one more person, really. So let's get started here. See, I need to mute somebody. I hear some echoes. Okay. So let's see here. So today's an open forum. So first, I just want to ask, are there any topics that anyone would like to bring up this morning? Any volunteers? Otherwise, I have some other topics I think we could talk about. No volunteers? You know, you guys really have to come with a few more ideas. So, okay.
Oh, well, I've got lots of things we can talk about. What would you like to talk about?
Well, I was going to talk about earth sciences topics, seeing how we've got like the Hawaii volcano blowing up and destroying houses, and there's been seems like a lot of catastrophe lately. So that would be something I might be interested in talking about. That sound interesting, Harry?
Not really, but go ahead.
Okay. Well, like I said, there seems to be an awful lot of catastrophe going on. So we've got some major activity going on in Hawaii. But my question is like, you know, why is the Earth structured like this? It seems like just below our feet is like this molten pool of deadly lava, right? So the question is, why is the Earth actually like that? I mean, you just drill a few hundred miles underneath the surface, which is like barely nothing, you know, like barely probably less than the width, the thickness of your skin, and you get some place which is completely inhospitable to any kind of life, to the point where you're just like a molten rock, so hot it bubbles to the surface. Now, I suppose the mainstream explanation for this is that when the Earth formed, it was like it came together from like all of these asteroids and, you know, boulders, and it just swept up all of that stuff in space. But I'm thinking that you know, a big boulder is a pretty cold thing, and if you put together two cold boulders, you're just going to get a bigger boulder, which is just as cold. And so if that was just the case, then you'd expect the Earth to be this big, giant, cold lump of rock, not this thing which is like boiling hot, molten lava just beneath the surface. So what do you guys think of that?
What makes you think these boulders are cold? That seems to me to be a fallacy on your part.
Well, I think, you know, we can go see these objects in space.
I don't know that any mainstream account says that.
Well, I don't know. I mean, you have to go and measure the. Well, we have been able to see things like asteroids. We've like had flybys and stuff like that, and certainly they do not appear to be hot. And certainly we have most of the things that are out in the universe are stone cold, like comets. Those are definitely ice.
But I think these are meant to be at a late stage. I mean, the nebular hypothesis, in terms of which maybe the galaxy and the solar system and the Earth were formed, basically ascribes very hot gases, perhaps undergoing thermonuclear fusion, which are sort of condensing and coming together. And after a very, very long period of time, then billions of years maybe, you get this cold stone. But I think that's the result, not the starting point. Well, at least that's the conventional view.
Yeah, I think somehow they're saying that heat is left over from the formation. But like I point out, like most of the things that you find flying around the solar system now, presumably like everything that's out in the asteroid belt, or like in the Oort cloud, those are supposed to be leftovers. Those are like frozen ice balls. So thermally, not a whole lot of energy there, I suppose.
But the Earth is still cooling. I mean, when I was young, we now talk about global warming, the media does, but we always talked about the secular refrigeration of the Earth, that the Earth over a period of time was cooling and cooling and cooling, and it would be a slow death. And that was the problem we had to address. Is
there any actual evidence of that?
I think over long periods of time, yes, there is. I mean, first of all, the Lord Kelvin's calculation of the age of the Earth on the basis of its cooling rate. He got a figure which was very much smaller than the figure needed for conventional explanation of, say, evolution and the formation of the Earth and so on. And the difficulty is that he only looked at the thermal gradients. He didn't take into account radiation effects, which would sort of accelerate that.
Well, I mean, I would consider evidence like you putting a thermometer in the Earth and over time observing that the temperature is dropping. That would seem to be a kind of an obvious thing. It kind of sounds like what you may be talking about there might be a calculation.
I think they say, I'm speaking quite conventionally now, I think they say that the very evidence that you started with, Franklin, that as you dig down, the temperature increases, that is an indication in itself, because it's actually the surface which is cooling over time. And then as you go down a little, you get a cooling, but not quite as great, obviously, because it's more insulated. So as you go deeper down, you're going back further in time to what the surface of the Earth was like.
But I think that the starting assumption that Franklin started with is false, in that the theory, as I understand it, regarding volcanoes is that the molten rock of volcanoes is due to the tectonic plates and subduction, and the molten lava is created by the subduction of the plate underneath another plate, and as that subduction occurs, this heat is being generated, and that's where volcanoes come from. That's my understanding, but I'm not a geophysical expert. That's not true.
Well, my question is, does that make sense to you? Does rock moving at like
you're asking
unimaginably slow velocity?
Hold on. Don't ask the question, does it make sense? That's not the correct question.
No, that is totally the correct question. We're scientists here. We're always asking that question.
The correct question is, what evidence is there to support that particular view?
Well, that's another good question. So what evidence is there to support that view? I mean, that is a very common view. So what evidence do you think is there to support that?
As I understand it, the evidence that they claim exists is that the volcanoes, when you do the ring of fire in the Pacific Ocean and that sort of thing, that they claim, based on not being a geophysicist and not really knowing myself, what the assumptions are that they go into making these claims, but they claim that that the volcanoes erupt and occur at the areas where these tectonic plates meet.
Well, see, that would be a problem for Hawaii because it's smack dab right in the middle of a tectonic plate. So that couldn't actually be an explanation for Hawaii volcanoes.
I don't know that that's really true or not, but I agree that that would tend to refute the hypothesis. But, I don't know what they're, you would have to look up and, maybe do a search. You're good at doing a search. Do a search and say volcano, source of volcanoes in Hawaii, and see what the official Wikipedia or whatever explanation of that is.
All right. So they're saying that the source of Hawaii is what is called a hot spot.
Right.
That somewhere there's just this plume that goes from the boundary of the Earth's core to just pop up in Hawaii. So, of course, that's not really explaining very much.
It doesn't really. The
other than just saying it's there because it's there, right?
Yeah, exactly. But you'll find out that a lot of this empirical science, where you don't have a whole lot of theory, and geophysics, I think, is one of those sciences where there's really not much in the way of a really good theory. But the theory is pretty primitive, and so you just sort of like, here's what we observe, and so this looks like this is the explanation of it. That particular thing that you mentioned sort of sounds to me like it's, because it's there, this is the explanation, and the explanation is valid because it's there. Seems sort of circular, I agree. But the real issue I think that you're getting at is what Ian was talking about, which is, you want to try to take this back to some theory of the formation of the Earth and the solar system, and if you try to connect anything that a current theory of geophysics, and you want to try to make it look like you have a valid chain of logic that connects the current theories about how the Earth is, and you have to go back, you have this chain of hypotheses that you have to go through. And of course, the first one is the Big Bang, okay? And, that's just kind of a guess. And yeah, the evidence to support it is pretty slim indeed. But, they don't really acknowledge that the evidence in support is slim indeed. Then you have, how galaxies formed. The evidence behind that is really, really meager and slim indeed. And so then the evidence regarding star formation, the theory there that stars condense from gas, that seems highly improbable to me. That seems extremely, extremely improbable. And they really have to work real hard to fudge the facts to make it look like that's actually something that's possible. That doesn't look at all possible to me. So then the nebular hypothesis, the stars are supposed to form out of this gas nebula and planets form out of that nebula. That all looks kind of, not really that credible. So we're sort of back to the question of, once you trace back to the theory of where this whole thing started from, that doesn't seem very credible. But since the evidence is so slim, you have next to none evidence, then you can't really falsify it. That makes sense to you, what I just said?
Yeah, I mean, I would totally agree that we try and find the logical stream of things. Again, an echo here again.
Well, the evidence is not even used to falsify it, because we have plenty of evidence that the tectonic plate theory of the Earth is not true. For
Yes,
instance,
I understand that.
GPS data shows the Earth is expanding every year, and it's not expanding because of stuff coming in from space, like meteors and stuff like that, dust. It's expanding too fast for that, but it's not expanding real fast. But when it expands, it causes the so-called plates to separate farther, and that causes the various lines of volcanoes that you see throughout the world. And also in the uh, limestone coral that's in the ocean, you see that the coral has rings, kind of like tree rings, and but they have more information than tree rings have because they have a ripple in the ring, and the number of ripples is the number of days in the year. And what you see when you look at the coral reefs in our oceans is that the oldest coral reefs have 481 days in a year, and the current rings have 365. So that is kind of like when you have a ballerina dancer, when they put their arms and legs out to expand, they slow down in their rotation rate, and that's what we see has happened to the Earth, but they won't pay any attention to that data. I mean, that's data on the history of the Earth. They don't want real data. They just want to use their idea of naturalism, and they want some kind of natural explanation for what caused it. And also, I don't know if you've ever noticed it, but most of the constants in science, in physics, for instance, can be measured to 8 significant figures. But because the Earth is expanding, the force of gravity is decaying, and we can only get 3 significant figures. Because if you take the strength of gravity at one part of the Earth and you measure it today and you measure it next year, you'll get a different number. You can measure it to 8 significant figures, but it's not reproducible. You can only reproduce it to 3. And so it's one of the few constants in nature that is changing all the time. And if you go to a different part of the Earth, like if you go in the ocean and measure it, you get a different value than if you measure it on the land. And so you got all those kinds of things going on too. And nothing in the current modern science explains, politically correct science, explains why the force of gravity is decaying. They don't even talk about that decay. And but we measure it and we can see it. Why don't they talk about it? Because it's not politically correct. It doesn't fit in with what they want to have. So
Bill,
yeah.
we know that the mainstream is they have a storyline, okay, a worldview storyline that I basically described previously. And anything that doesn't really fit into that storyline, they can't really make it fit logically. And so, in order to not spoil the storyline, it's convenient to just ignore it. That's my thesis, which you call it politically correct, and I agree that it's enforced politically. Yes.
What they say is that any data that doesn't support their theory is no good.
Correct.
For instance,
that leaves them in having to admit that they don't know. And that's one of the things that I really don't like about scientists is that they always have to have an answer, but they can never say I don't know or we don't know or admit that they really don't have an answer or that they really don't have a good theory. And so that kind of puts them in the position of having to have an answer, even though it might be totally wrong and obviously contradictory to facts.
So this whole story, so I've got this website up here about how do planets form. So this thing could potentially just be a fairy tale. That it's like, it kind of sounds plausible, but like you said, I don't see it conceivable that something as big and as large and as hard as the Earth could form out of a gaseous cloud. Gas is not a solid. Most of the gas is things like helium and hydrogen, which don't form rocky planets. Now, so you'd have to be a little bit more sophisticated. So I think the mainstream might also say that that the suns do gather up the hydrogen and the helium, and I could believe that. And once it ignites, then it can convert it into some of the heavier elements. So, but you can, generally speaking, only get up to like carbon, oxygen, maybe in the sun. But then it takes like a supernova explosion to create.
As you mentioned that, there's a new report that just came out recently where they reported that the traditional theory of a supernova isn't true. And I thought, that's really kind of strange. They're claiming that they observed the remnant star of the supernova, which to me seems sort of, I'm not sure I can understand what they're talking about. But what they're saying is that there's a companion star that sucks all the atmosphere off of the primary star that goes supernova, and the supernova occurs after it sucked all the hydrogen off of the companion star. So there's two stars, it's a binary pair. And, and I'm looking at this and I'm thinking, well, how can you explain how heavy metals came from with this scenario? So the story that they're telling, it doesn't really seem to be consistent with their theories at all.
Well, also, if you look at the temperature of the sun, we see from time to time eruptions on the sun, and we can see a little farther into the center. And what we discover is the center of the sun, where things are supposed to be hotter, are actually a lot colder, thousands of degrees colder than the surface of the sun, the ionosphere of the sun. And so their theory of the formation of the solar system does not agree with our current measurements of temperature. And they just ignore that.
I think conventionally they would also say that all the planets in the solar system were originally gaseous. And gravity has obviously an effect here, because up to Jupiter, you have the terrestrial planets, including the Earth, which are formed of are solid. But then you have starting from Jupiter, you have all gaseous planets thereafter. And I think they might say they're in the process of transforming as well.
Yeah, they keep the story going.
Yeah, I suppose so. But by the way, just a quick comment on this political correctness business. I mean, I quite take the point, but I think in probably the majority of cases, all this political correctness, which annoys us every day, is probably not in science caused by definite conspiracy. I think it's just by default. I mean, you have the whole establishment, you have academic careers over 40, 50 years which have been built up painfully on certain orthodoxies. And if a professor who's at the height of his position in some university or something has his whole foundation questioned, the whole lot will come down. And then you have people on the career ladder going up, and then you have people supporting them, the politicians, the journalists, the common people who love to look up to an expert. So political correctness can be used to, in a deliberate way, if you like, to fool the people and to put forward certain views. But I think in most cases it's merely by default. It's just what I would actually say laziness and intellectual treason of the leaders of our society, the so-called intellectuals of our society, and of course the people who follow that, the journalists and the media and the rest. That's a comment.
Well, I think that the scientific method is somewhat defective, and that's a large part of the problem. That's my thesis. That's what I would argue for. And the method doesn't really work very hard at allowing actual questioning of the prevailing paradigm. As you said, the way they go about doing things, the political, the way you get promoted and the way you get government funding tends to bias science in favor of the prevailing paradigm and not in paradigms that challenge the prevailing paradigm. Does that make sense to you? Does that sound like what you were saying to a certain extent?
Yes, yes, it is sort of consistent, I suppose, Harry, with what I was saying. I was also thinking, though, in view of your important point about the scientific method being defective, and we've talked about lack of logic and all that sort of thing. But I think what they're doing in practice is even worse than what they claim to do. I mean, if you look at their claims to using the scientific method, you might find that there are some elements of it that we would question. But I mean, most of it probably would be unexceptionable. But I think they're not even following what they claim to. I mean, if you applied a simple scientific analysis to, say, the special theory of relativity, I think you'd come to the conclusion that there's a fundamental flaw with it. But they're not doing that. They're not even applying their own principles.
Yeah, that's interesting. I think that's what Bill is saying.
Yeah.
Okay.
It's
a two-pronged thing. Two-pronged.
Scientific theory methods that we've had: the existential scientific method and the postmodern scientific method. Both of them take away falsifying of theories in science based on false ideas. So if your ideas, your assumptions are false, they don't falsify the theories anymore based on that. But then when it comes to falsifying it because it doesn't predict the right data, look what they did with general relativity theory. It couldn't predict the velocity of the outer spiral arms of spiral galaxies and the velocity we measured in our own solar system with some of our rockets that went out toward the edge of the solar system. And so what they did is they invented dark matter and dark energy, which we had never seen. And they claimed that there was 24 times as much dark energy and dark matter as regular energy and regular matter. So they wouldn't have to falsify the theory of general relativity. Well, that's not the way to do science. And in my own work, when I derived the force of gravity from electrodynamics, the force of gravity perfectly explains these velocity of the outer spiral arms of spiral galaxies and the acceleration as you go out from the center. And you don't need dark matter and dark energy. But they didn't. They should have falsified general relativity according to the rules they were following, instead of inventing a fudge factor so that they wouldn't have to. And so we see that over and over again in the modern scientific method. And no one is calling the scientific community to account, saying this is not true. We cannot make progress if we do this science this way. No one is really doing that who has any authority or control. And so it's a shame. We're spending more money on scientific research than we ever did in the history of the world, and most of the major theories we're developing are all false. And by the way, if you come to the conference, I will be documenting that in some of the talks, presentations I'll be giving. I'll do the major theories, the theory of the force of gravity, the atom and the nucleus and elementary particles, relativity, quantum mechanics, all those theories we know are false, but we don't admit it.
Okay, Bill, back to the expanding Earth theory. I think that as a practical example, this is an interesting case in point. And I know that David has been talking about this, and I believe at the last conference, which was in Vancouver, the fellow from Australia talked about that, and I can't remember his name. Did you go to that, Franklin? Did you listen?
Yeah, I did. Mm-hmm.
Okay. Now the question, well, okay, so we know that that's an alternative theory to the prevailing paradigm. Okay, so here we have a case of a paradigm that is presumably challenging the existing paradigm. So the question then is, I guess if we're going to reflect on scientific method, how is that being dealt with by the establishment? But my real question to Bill was, in this alternative paradigm, the expanding Earth paradigm, what do you know, or can you answer my question? Here's my question: is there a molten layer beneath the crust of the Earth in that theory? And what is the explanation for that in the expanding Earth theory?
Yes, there is the molten layer below, and even further to the center of the Earth. We can see that by uh, setting off shock waves in the crust of the Earth and monitoring the bouncing back from each of these layers. So we do that. They do it a lot in oil research and stuff like that. So they're very familiar with that process. So they want to know where the oil is, but they see the other layers too. And uh, and it seems to be the decay of gravity that is causing the expansion, which causes the cracking at the surface so that the things underneath. It's kind of like a balloon. If I fill a balloon with gas like hydrogen or helium and let go, it goes up into the atmosphere and expands as it gets higher because there's not as much pressure holding it in, and then it pops, which in our case would be a crack in the surface of the Earth, and the stuff that's underneath the surface comes out. And that's what seems to be the case. And also, in history, we have recorded the size of the moon, and that we can see from the surface of the Earth. And what is happening is the moon is getting smaller, as far as we can tell, because it's getting further away from the Earth, because the decay of gravity allows it, with the energy it has, the momentum, to do its orbit farther away. So what we see today when we look at the planets in our solar system is a lot smaller than what they saw in the past, and they didn't need a telescope or anything like that to see the various planets and some of the moons of those planets. But today we need binoculars or a telescope to see it because it's too small. We cannot see much detail, and so we hit the.
So the big paradigm in your thinking, the main paradigm, or the main concept, the main conception behind the paradigm is this change in the gravity.
Yes, and the decay of gravity produces radiation. And when you calculate it, you discover, oh, that's the cosmic background radiation that we see. So that explains the cosmic background radiation. Right down to you can plot a graph of it, and you see it's exactly what we measure. So they use the cosmic background radiation in politically correct science as the basis for the Big Bang, whereas if you take into account that gravity is decaying and it's really electromagnetic in origin, then you can predict this radiation. And so that's something that when you're supposed to follow the idea of simplicity in science. If you have one theory that explains all this data, well, that's probably better than having a whole bunch of theories that partially explain the data. And but they don't want to use those kind of criteria anymore. They want to. They have political goals in their science that they want to accomplish, and so that's why that drives them to only select certain types of scientific theories that they want.
So talking about expansion tectonics, so we do have a summary of last year's conference here on our website. So So it was James Maxlow, who was our special guest speaker last year, and he gave a talk on expansion tectonics. And there was also some talks on the actual mechanism by which the mass might increase inside the Earth. But I bring up this topic in that just intuitively, none of the existing explanations would really explain why the Earth is so molten hot, so close to the surface, and so much of the volume of the Earth. I mean, it's like we're living on top of a sun, basically.
Well, Franklin, that could be, one of the things that you can deal with that pretty easily would be to say that the Earth is affected by tidal forces, which put stresses on the crust or in the outer layer. And so that generates a lot of heat in the just below the crust of the Earth due to the tidal forces. So you could say that the tidal force of the moon is dissipating there. So, there's some simple ways you could talk about it, and probably a lot of different ways you can explain it.
Well, yeah, there could be. I mean, certainly the moon Io is an example of that kind of tidal heating, we think. Although around the Earth, I don't think that the moon would be enough of an influence to cause any kind of heat. I mean, we have to talk about these things intuitively, because there's no way I can prove one way or the other that there's just not enough. All I can do is just kind of eyeball it and say, no, I don't believe that either, kind of thing.
Well, one thing
you kind of base with the problem of that you could probably generate a lot of theories and not be able to falsify any of them because the data is very meager.
Well, we have data which is not taken into account, and that is the age of the Earth. It's currently reported as 3.5 million years or something like that.
4 billion years.
Yeah, but like radioactive decay data, none of it gives an age of that, because they don't do the age determination correctly. They do the age determination using radioactive isotopes with false assumptions, which don't falsify their theory, but they are known to be false, which give you an older age. And when you remove those false assumptions, you get the age of the Earth is rather young, on the order of 10 to 12,000 years maximum. So that they don't want to acknowledge that data. And I've worked on that data. We worked on with some other people at Oak Ridge National Laboratory. We worked on radio halos, and radio halos, when you look at a mineral, let's say you have a mineral that had uranium in it and it decayed to lead, and you were looking at the amount of uranium left in the mineral and the amount of lead, and you assumed all that lead came from that uranium, and there's about the same amount of lead as uranium, then the age of the Earth is approximately half of the half-life of uranium. But if you look at the radio halo patterns in there, you discover, oh, we didn't just have uranium, we had hundreds of nuclear isotopes that also decayed to that same lead, but they had much shorter half-life. Some of them days, some of them months, some years, some hundreds of years or thousands of years. And they all made a contribution. But you can see in the radio halo patterns, you can see how much you had of these different elements. And when they do that, they get a very young age. Well, they don't want to do that. So they don't even acknowledge the existence of radio halos. They pretend that that doesn't exist, but it was measured at their laboratories, and they don't want to admit that. And people like Robert Gentry and myself worked on that, and so there's just a lot of manipulation of data, refusing to consider certain data, and that sort of thing that goes on in the scientific community. And if you make a big deal of it, guess what? You're fired. You can't get a job anymore in that field. And that happened to Robert Gentry. It happened to myself. It happened to all kinds of people. It's still happening every year. And it is crazy what we do. and but uh, the politics is a lot stronger than it should be in science, and it drives the goal of science.
So I found the Radio Halo website here, so you can look at that. Although it still doesn't seem to explain. I mean, there are some other mainstream explanations for why the Earth's core is so hot. So one of them is that it's from radioactivity. So all that heat comes from the decay of like these radioactive elements, such as uranium, and so that causes the incredible hot heating. Because, like I said, I don't think it's logical that you have all these lumps of, iron and silicon and stuff like that just kind of coalesce into a cloud. Because I think if you did that, you'd get a big cold ball of, carbon and silicon and iron. So, but if there was a lot of the heavier radioactive elements, then they would perhaps collect into the center of the Earth, creating this really hot ball. But I would think there would have to be a lot of radioactive elements for that to happen, such that the molten lava is just right beneath the surface. I mean, that would mean like the Earth is like 98% like near molten state, right? And intuitively, I just don't see that being enough energy
in certain places, though, Franklin. That's kind of the problem. You sort of have to explain why aren't volcanoes everywhere? Really, really common. That's not really the case. The volcanoes in the United States, if we talk about it, as I understand it, the primary area is on the West Coast and out there where you live, right?
Mm-hmm.
And then there's an active region around Yellowstone National Park, but I don't think there are any volcanoes anywhere else. There may be some older ones, but so basically the majority of the continental United States, there are very few volcanoes.
Yeah, but we do have one sitting right in the middle of Yellowstone, which is right in the middle of the plate. But they're also saying that that's kind of like a Hawaii kind of thing.
But if you think about, the volcanoes aren't that common. I mean, you'd think that there was all this molten lava underneath this crust of the Earth, that they'd just be popping up everywhere. I mean, that would be my view of it.
I think they would say that in ancient times, they were very predominant, and that it's only the world at present is indicating that it's the exception rather than the rule. I mean, we've talked about, I think in a previous conference, things like basaltic columns forming, say, things like the Giant's Causeway. Well, there are no volcanoes in that area at all now in the whole country. But I mean, in ancient times, that's the general theory, that it was the lava coming out of the volcanoes that cooled and formed these columnar structures. So I mean, you can see these sort of fanciful pictures of the ancient Earth with volcanoes all over the place, all over maybe what is continental North America now, and all over Europe as well. But by the way, just one other thing, I mentioned earlier, I think Franklin captured it as maybe like laziness may be the explanation in most cases for political correctness and not analyzing things. And that is true. However, there is another thing which is actually quite unfortunate, and I was just thinking about it because I had a quick look at this Radion Halo business, and I saw arguments ad nauseum on both sides, and you could spend your whole life studying it, and you could come to either conclusion, and experts have come to either conclusion. And it seemed to me that this, without going too deeply into that itself, but it's one further example of maybe a worrying phenomenon that we ought to admit, that actually there's no such thing as objective science, that all opinions are formed ab initio for emotional reasons. Like, people want to believe the Earth is thousands of millions of years old, or people want to believe that it's 10,000 years old. They make up their mind, and they've established that. And that all the work they do after is merely justifying their initial prejudices. That it's the emotion that comes first, not the science. And that we're all guilty of that. I mean, dissidents are possibly guilty of that. Maybe because we didn't want to believe what authorities say or something like that. It's just a worrying phenomenon, because it would indicate to me that our ability to reach rational truth is limited, because we have this fundamental prejudice already in our brains, which directs us in a particular way, and that is why we very infrequently agree with one another, because we're all starting from different emotional premises. So I just thought I'd mention that as well.
All right, so I found a diagram of the structure of the Earth here. So this is the conventional view. So we have like a rigid mantle. So presumably all this lava is coming out of this rigid mantle. And we have a stiffer mantle, and we have an outer core, which is liquid, and an inner core, which is solid. So that is the layers that they think that are in the Earth. But all these layers are remarkably hot. You don't have to dig very deep, actually, to experience the actual heating of the Earth. That's pretty obvious. So I'm just speculating that I suppose any of these explanations could, but I suppose I could also put forward another explanation, which is that, you know, it's actually being powered by something. So that would be a little bit along the lines of the nuclear caused heating. But we also have to try and account for the apparent expansion. I think that was one of the things that was mentioned by one of the other speakers in our previous conference, that if there's some sort of mechanism for mass generation, that is probably may also be a heat source. So in some ways, you know, I mentioned like it's like we're living on top of a sun. That I'm kind of suggesting that there is literally like a sun, a nuclear furnace of some sort inside the Earth, and that is what is driving all of this heat. I don't think it would have accumulated naturally from things just falling together. I don't think there's enough radioactive elements to cause that degree of heating. But if the expansion of the Earth is a true mechanism, it's due to, say, the increase in mass and due to some kind of nuclear process that releases heat, then, well, no, that's complete speculation, but it would just seem to make a little bit more sense to me if that were the case. Then we could explain, you know, the heat, and we could explain the mass increase in a more intuitive way. Like I said, that's complete speculation, but it's trying to we're just trying to find ways to.
What are you saying is at the center
things.
of the Earth, Franklin?
Hmm?
What's at the center of the Earth? That core thing that they call it. They call it the core.
The core, yes. Well, that's
inner core, outer core, surfer, whatever. I can't read it. Something.
Yeah, most of the core is made out of iron. They think.
Well, I'm just asking. What do you think?
It probably is made out of the heavier elements, like you know, iron is one of the more common elements in the universe. So I have no problem believing that. But I would also believe that, you know, for, you know, due to the way I think how atoms are formed, and that it's fairly easy to do nuclear fusion. That what's going on in that inner core is actually some nuclear fusion. The nuclear fusion is, I would say, pulling mass out of the ether. So that's where it gets its additional mass. So it's fusing, or it's creating, like starting with protons, which are hydrogen, and then it's continuing to actually fuse things together into helium and oxygen and additional oxygen and iron and other elements.
But is there any evidence for that, Franklin? I mean, we know that there's fission taking place within the core, but I mean, you've made this quite analogous to a nuclear fusion generating star. Is there any evidence that there is actually nuclear fusion taking place?
Well, I've done that on my own because, you know, there are experiments showing that you can take oxygen and carbon, and by just merely sparking carbon in oxygen environment, you can create iron. And I've done that. I mean, it's fairly convincing, and that's really low energy triggered fusion. So if that can be fused at that low in energy, then it's not inconceivable that that kind of fusion could be happening in the Earth, is what I would say. I mean, some examples of another example of carbon arcing would, of course, be a carbon lamp, and that thing is like spectacularly bright. I mean, it's way brighter than what one would expect from just normal incandescence from the heat from the electrical arc. And I'm speculating that the reason why it is so bright is because that is actually a release of fusion energy, mostly in the form of visible light. So it's very clean fusion. It doesn't produce any radiation except for the kind of radiation you want, which is light. And there's also some other things that, if you go to these ion recyclers, the way they recycle it is by using these gigantic carbon rods into these vats. And the secret element to make this work is oxygen. The more oxygen you stick into this thing, the hotter it gets. And I would suspect the reason is not because oxygen is burning anything, but oxygen is the required element in order to promote what I would think is a fusion process. So that's producing so much energy that it makes it very efficient to melt down these vats of scrap steel. I mean, when I look at the calculations of what is the theoretical amount of energy it would take to melt that stuff compared to the amount that is put in, it's only about twice. It's only about twice the minimum. And I think that's pretty remarkable. I mean, there's very little, for an open vat kind of process like that, I would think it would take like 10 times the theoretical amount of energy to melt those things, but only takes double. But of course, that's just kind of, just shooting off my mouth. But still, I think that's a possibility. This is one of the things that I work on in nuclear physics, to show that things like nuclear fusion are actually a lot easier and simpler. So, but who knows what's going on in the core of the Earth? I mean, it's not like we can go there and see what's going on. But all I can do is speculate and try and figure out some possible ideas for why we observe the things that we do.
The bottom line, as far as I'm concerned, is if you have limited facts, and that implies that you can have more theories that fit the facts. The idea, what I'm assuming, is that if you have more facts, it constrains the theory to, a larger set of facts that it has to be consistent with. But if you don't have that many facts, you can speculate on a lot of different theories. I don't think that there's a lot of facts as to what the structure of the Earth is like. The only probes that they have that I know of are these seismic measurements that they do. I don't think there's anything other than that.
Yep, that's all we really have. I mean, we have people digging into the Earth and just measuring the temperature rise. We have seismic waves, and this picture here is probably based on that data. But there are people who think that the core of the Earth is actually hollow and things like that, and they have their viewpoints. But because what we can see in these seismic waves, we can see boundaries. I could believe, yeah, we can definitely see boundaries. But what's inside those boundaries? What is the actual evidence that that core is iron? I'm not quite sure what the evidence is there for that, or what the rest of these are made out of.
They look at the total mass of the Earth and try to figure out what the density is. And so presumably, since iron is a fairly dense material, they can make the average density, kind of work out, if you will, by putting a lot of iron in the center. Does that make sense to you?
Probably. They're probably doing something like that.
Yes, and I think you can get similar diagrams for all the planets in the solar system up.
Right.
It's not specifically terrestrial measurements that are determining this. It's, as Harry says, sort of an estimation based on densities and.
Well, actually, I'm not sure that's true, because we just sent a probe to Mars, and one of its primary goals is to actually drill into Mars and stick a temperature probe into the ground and try to actually measure the same things that we measure here on Earth, I think. So they're trying to take the temperature of Mars. Obviously,
they're trying to verify or hopefully falsify a theory that they already have, because they've had a similar diagram to this for Mars, for maybe 100 years or more, without having taken any measurements. So we'll see if those measurements actually verify what the received opinion is, or whether it contradicts it.
Well, I'd be surprised. Let me see if I can look that up. See, structure of Mars.
Right. This is a very interesting theory, though. But the real problem, it seems to me, is why aren't there any volcanoes on the moon?
Yeah, why aren't there any volcanoes on the moon? Well, we know there's volcanoes on other moons around other planets, but there are no volcanoes around the moon. Now, there are a bunch of theories about where the moon came from, one of which is that there was some titanic collision, and the moon is a remnant of that, which means that the moon is largely the top layer of the Earth. So in some ways, it doesn't contain, theoretically, the heavy stuff of the moon. Although I would be curious to know, do we have any thermal data on the moon, or is in fact the moon just a cold?
I think they know something about that from the Apollo missions, but I don't really know. I think that's been studied as a result of the Apollo missions. And that's why they were so surprised, when they discovered these volcanoes, and I think Io is the one, that was a real surprise. And I think Titan, didn't they, they've discovered all these unexpected things. And the reason, those are such a surprise is because the moon, they don't really fit in, their thinking that they had established based on the moon is kind of like basically a dead planet.
Well, some of the things with the Earth expansionist people show is that they can also show that same kind of activity on the moon. So whatever is causing the Earth to expand appears to be causing the moon to expand. So like on the moon, you can see there are areas which have lots of craters, but there are certain areas which appear relatively smooth, and I think those correspond to like the like the areas where they may have expanded into. Let's see here, we got someone needs to be muted here.
Well, the idea is that the lunar highlands, which are supposed to be older and are composed of a different material, and then you have the plains, which are the Maria and the dark areas, are supposed to have been formed by lava that surged forth from the beneath the surface. But as I understand it, I'm not an expert on the geophysics of the moon, that there really isn't much of any seismic activity. There is some, but it's not really super extensive. And so that's kind of a mystery because there doesn't really seem to have been any significant change in the moon, no volcanoes. There doesn't seem to be anything happening. The surface seems to be, when a crater hit it millions and millions and billions of years ago, it's still there. It's not, so nothing is changing really. And that's kind of a surprise.
Yeah, but the Earth, the moon's smaller, basically just because of the size would be a reason that I would think that there would be no volcanic activity. The surface has got no atmosphere, no rain or anything like that to change it. But basically, all this energy comes from the force of gravity, and since the moon is smaller, the force of gravity would be less, and it wouldn't have the energy to have a hot molten core. If you take a meteor or anything, take any small object, and there's no volcano going on in them. So I think it's mainly just generally the size of it and the amount of gravity involved.
Well, here I just dug up a picture of the moon. Apparently, even the moon has a liquid core, according to latest seismometer data.
It seems to be from the couple of diagrams that you've put up, Franklin, that the singularity with regard to the Earth is that the Earth has a very thin crust, that in the case of the Moon or Mars, you have a very, very thick crust between the surface and any molten center.
That's not true, because if you look, there are what we call seas on the Moon, and that is due to the three-dimensional expansion due to the decay of gravity. And so we have plenty of evidence that it was molten at one time and that it expanded, and you have the equivalent of continents with seas. And so does Mars has that too. So we do have evidence that it was more molten somewhere at one point in the past. But those seas, there's no water in them. There never was any water as far as we can tell. And they just solidified.
You just said that the moon is expanding, and earlier you said that because the moon's getting farther away because of the decrease in gravity, it's decreasing in size. So those two don't go together.
No, the force of gravity between the moon and the Earth is decaying, because as gravity decays, it gets further away. But
okay, so saying the visible size of it is decreasing, not the physical size of it.
That's right. The what we can see, because it was a lot closer to the Earth in the past. And but you see, the under the Big Bang, basically everything starts out hot, and then it cools off, and it should shrink. But what we see is they didn't shrink; they expanded. And
we really have no evidence that it was actually closer to the Earth at an earlier time.
Oh, yes, we do, because size was measured that you could see from the surface of the Earth. It was significantly, if you read the historical accounts, people really were impressed with the size of the moon. Sometimes if you see the moon when it comes up over the horizon, it'll be twice as big as it is when it gets further up in the sky. It looks much more impressive. Well, it was much more impressive in the past. And,
well, yeah, I mean that's kind of just more hearsay, not really scientifically measured, is it? I mean, I was looking for scientific information that measured the size of it.
Yeah, they did. The ancient Greeks and other people measured the size. They didn't have telescopes and stuff like that, but they had things that they could use that by eye and measure the size, and the size was significantly larger than it is today.
Yeah. Okay. Well, I would say, if I hold my thumb up and see how much I can cover of the moon, and then you hold your thumb up, I think we got a pretty inaccurate comparison system. So, I just I'll take that with a grain of salt as far as.
But if we have a stick that's a certain size, and we look through it and measure the width of the moon across the end of the stick, let's say it was measured in inches or something like that, you could see in the past that it was wider on the stick than it is today when it's
Okay,
particularly
but you have no empirical information is what I'm getting at.
yeah. So that is empirical. I mean, it is measurement in whatever their units were that they use, and so, but we don't pay much attention to the data from the past. We look at our own data from
But it
our.
doesn't sound like we have any data from the past.
Oh, we do. Did you know the data was removed from college textbooks in the United States starting in the year 1900?
So that's where the ancient Greek data went to?
The Greek data was
Who-
we had some of that in our textbooks. It was in Encyclopedia Britannica. It's all been removed. And
Oh, so that's where you got the information from, was the Greek data that you found.
pardon?
I'll just take it with a grain of salt.
Well, just get yourself an old copy of Encyclopedia Britannica from before the year 1900, and you'll be amazed at what's in there, because it disproves what our scientific theories say today. That's why they took it out.
Actually, Bill's really, it's really interesting to get old copies of the Encyclopedia Britannica, and a good source of information, actually.
Yeah. What happened with Encyclopedia Britannica? It was bought by a party, and they did not like, they wanted a different agenda for science and wanted something different to be politically correct, and so they removed it from all versions of Encyclopedia Britannica after that date. And we had colleges like the College of William and Mary in Williamsburg, Virginia, where I went, that have books from before that time, and they have a very different data that they present than what we have.
Okay. Can I ask, Bill, for what you're saying is that the Earth is expanding in size but decreasing in mass.
That's right.
Okay.
Yeah, and that's what we measure. We measure the force of gravity, big G. Big G is decreasing.
So if it's increasing in size and decreasing in mass, then new matter is not being created within the Earth, is what you're saying. It's just expanding the existing matter.
No significant amount of matter. I mean, we do have meteors coming down. There's a slight increase in terms of the amount of material, but and when you look at the theory of gravity from electrodynamics point of view, what happens is when the radiation is given off that produces our cosmic background radiation, it starts with all of the atoms and all of the matter of the Earth. Well, the atoms that are in the center of the Earth, they don't escape. They're reabsorbed. Only from the surface of the Earth do they escape. And so what happens is the surface of the Earth cools off and does a lot of things which don't happen to the center. The center stays more massive. In other words, if the mass of rocks on the surface of the Earth is lower than the mass of the same rock a mile or two below the surface. And so.
I mean, I was under the impression that mass was basically determined by the atomic structure, not by if a rock is made of the same molecular material, then I would think that the mass of that molecular material would remain the same regardless of where it's located on the Earth.
No. And not only that, did you know that the Russians and the Chinese have measured the temperature dependence of mass?
Yes, I knew that.
Yes, and it changes with temperature. It increases with E = mc squared, and then it drops off and increases again, because if you know what the origin of mass is due to the vibrations of dipoles and other multipoles in atoms, and even in elementary particles. And so when the vibrations decrease for some reason, because they radiate some energy off, the mass drops. And if you have a good theory of elementary particles, you can predict the mass of all the elementary particles just from the vibrations of the material that make up the elementary particle. And the ancient Greeks called that monads, and the Indian Jains also called it monads. And we, in 1900, we changed that to atoms, chemical atoms.
I'm just basically trying to establish the two different theories of Earth expansion here that seems to be going on in the conversation. And one is that there is matter and being formed within the Earth that's causing it to expand. And the other one is that matter that exists is
Maxlow. Maxlow, I think, advocates that point of view.
Yeah.
Okay, well, I think that's what Franklin was also just saying, is that there was matter was being created within the Earth.
Well, matter. The argument that Franklin gave is not valid, because when you take two lighter elements and you combine them together to form a heavier element, the heavier element occupies less space, and its mass is less than the sum of the masses of the two lighter elements.
Correct. Yes.
So you would lose mass if you did that process.
You'd have to
Well, I'm also saying that you're actually pulling mass out of the ether. You have to have a source of the mass. You cannot create mass.
You're actually saying you're actually creating the lighter elements that you're creating the heavier elements from are being created as well.
Yeah, I mean, you have to start creating the lightest elements first, and then as long as you have a steady supply of those lighter elements, then it doesn't really matter what the relative weight is. I mean, you're adding weight onto weight. Right?
The ether doesn't seem to have much effect on the inside of large bodies like the Earth or the Moon or the Sun, but it has an effect more on the outside.
Well, I mean, that's the debate. I mean, I'm saying possibly that's the source, because I personally feel as a materialist that you cannot create mass out of nothing. So if Earth is gaining significant amount of mass, it must be getting it from somewhere. And so I think the ether is a material substance. It's just positrons and electrons. It can use that as its feedstock.
Yeah. Well, mass can be created out of solitons, standing waves of the electromagnetic field. We know that by experiment. We don't know that by experiment from the other approaches that were mentioned. And so the only one that's experimentally verified is what Bostic did. And that was very significant, I think, that he measured that. And now we're able to perform further experiments to further confirm many of the conclusions that gives rise to.
Oh, you're saying something in Bostic's theory allowed electromagnetics to directly create mass and maintain it?
His theory, his experiments, he took electromagnetic fields and made what are called solitons, and he put two or more solitons together, and he established mass. So he had no charge, nothing but the electromagnetic field, the soliton, which is a kind of a semi-permanent standing wave, the strongest entity we have ever found. We can put a soliton in a nuclear reactor when everything associated with a nuclear reactor is coming apart due to the radiation. The soliton is not affected at all. Because
how was he able to establish that he created mass?
Pardon?
How was he able to establish that he created mass?
Because you can combine three of these solitons and make an electron with its mass.
Did he accomplish that?
Yes. And he published papers on that.
And the electron persisted?
Yes.
I mean,
and the only way to get an electron is to bring a positron next to it, and then they both will disappear back into the field.
In mainstream, this is called pair production, where you take two gamma rays, which could be considered, electromagnetic wave, and if you put a gamma ray of sufficient energy near the nucleus of an atom, that will cause positrons and electron to pop out of seemingly nowhere. And that is the opposite side of the equation for E equals mc squared, and that is claimed to be a conversion of energy into matter.
Right.
Although my interpretation of that is that that's just causing matter to be released from the ether. I don't really believe that it could be created out of nothing. That a wave could create matter.
Yeah, it requires the catalyst of a nucleus to create change the energy into a particle. But I'm not sure if that's what Bill is saying, that there was a nucleus nearby.
We claim we're doing this in a vacuum.
Yeah, what's Bill doing is claiming is very different.
So what was he using for an energy source? I mean, do you have reference to that material so a person could follow that particular experiment?
I have some of them. They're on. If you do Winston Bostic solitons, or Google search, you'll probably find more of them. But they show pictures of what a soliton looks like. And by the way, the concept of charge was shown by Winston Bostic to be an approximation, because the soliton is not something that is confined to a small volume.
Well, if he was able to create a mass, I'm particularly interested in the experiment in which he did that. If there's some reference material that you could share, I would appreciate it.
Yeah.
Well, just did some Googling here. So here's something from Winston H. Bostic, experimental study of plasmoids. So though the abstract doesn't really say anything about creating mass, it's more like creating things like spiral galaxies and things like that. I could believe that you could create stuff like that.
Well, he's trying to show that the field can be the source of all material in the universe, including galaxies and not just atoms and elementary particles. And
yeah, I'm fully in agreement with all of that. I just find it amazing that he was able to accomplish that. And that's where I'm looking for his experiments that would have accomplished that, because for us to control the energies and the coordination of energies required to create matter is quite phenomenal, I would think. I think that's something that nature can do with its tremendous powers. But for us to be able to do it, I would like to know how Bostic did that. And
well, he also had the concept of making a container out of these plasmoids that could control thermonuclear fusion, because it's strong enough to hold it. But his problem was he couldn't make the geometrical shape out of the plasmoids that he wanted. It wasn't a bottle. It was a shape that he couldn't control very well. So he could make a particle, but he couldn't make a bottle, which is what his grant was to do that.
Well, that kind of makes sense. Like I said, I don't find it very interesting that we could actually control the energy required to do something like that. Apparently, he tried, but it was unsuccessful too. But it's just interesting that he created mass. That's why I'd like a reference, if you could find one and you can share it with us.
Property of the plasmoid. The mass was a property of a plasmoid structure, and it was the vibration of the structure that produced the property of mass. And from electrodynamics, that agrees 100% with what electrodynamics would predict for the force of gravity. If the force of gravity, due to vibrations of electric multipoles made of plasmoids, then you would predict the force of gravity, the proper strength of gravity, and you would predict the fact that gravity can decay, and you would predict what the decay would look like if your mass was a certain amount right now for that.
Okay, but again, he was using plasmoids, which already have mass, and he was just showing that by vibrating, and then you can increase or decrease that mass. That sounds like much more like what the Russians were doing with heat and cold.
Yeah.
Well, here's a reference to plasmoids here, but he was just like firing two plasmoids to show that they can form galaxy-type formations, spirals. But that's not what we're looking for, actually. There.
No, because you're already starting with mass when you're starting with plasmoids. I mean, plasmoids.
Right. This was a different phase of his work. The if you have the concept that everything is made from the electromagnetic field, then you should be able to describe the formations that we see and the shapes that we see astronomically. And so that's what he was trying to do after he was not able to make the container that could hold controlled thermonuclear fusion.
Yeah, I can go along with the fact that fields are what creates the mass and that, but I was just more interested in it having actually been physically done, and the fields have been controlled to the point of creating mass. Here in the plasmoid experiment, they're just actually taking mass and changing the characteristics, the amount of mass based on the vibration of the plasmoids.
Because the ones that don't have mass, solitons, plasmoids, are made of plasma.
Right, but solitons are, basically theoretical, not physical.
Well, solitons can be made in any fluid, water, air, as well as electromagnetic field. And the electromagnetic field was the properties of the electromagnetic field were measured by a can't remember his name, a scientist at Caltech. He measured there were 3 kinds of electric fields and 3 types of magnetic fields, and he measured 13 properties of each. And and one of the properties is that there is a strength of the field that causes all electric fields in the universe to be connected, and all magnetic fields, and it's equal strength. And so that was something that we don't normally take into account in our scientific work today. But that was.
I don't have any problem with the field concept in that, except for the difference that we describe is you have a field which you call the life energy field, which I just consider this to be a longitudinal field. But other than that, I mean, all of these are theoretical. But I was wondering if Bostic had actually controlled those fields and created mass, or if it was a theoretical process that he'd worked through, and not necessarily a physical one. You're saying he actually physically created a tiny bit of mass, and I don't know exactly how.
By mass, he created things like an electron. An electron is one of the simplest of all known elementary particles. Right. Consists of 3 solitons, and each soliton has a charge of E/3.
Right.
And that's what we measure experimentally when we measure by scattering experiments off of electrons or protons or neutrons. We measure the fundamental unit of charge that is involved in the structure, and it's E/3. And so you see that in the charge of different.
But charge is again not mass. Charge is basically associated with a mass, but
but charge is not a fundamental quantity, because a soliton, if you look at it in something like water, where you can see it much better and much bigger, you see it's like a hurricane or a tornado. It has a shape and a certain size you can see, but you can also see that it extends way beyond that. And so the concept we have of charge is that charge is finite. And
Well, that's the concept that mainstream has of charge.
yes, and but charge is a property of a particle, let's say, and that particle has a finite size, and we don't let it be extending thousands or millions or billions of miles. We don't give it that.
I don't see that mainstream doesn't do that too. Mainstream also says that there's a Coulomb's force that extends out no matter how far out you go. A charge can be felt. So I don't see where the mainstream is saying
when you
anything different about that.
Coulomb force, you're calculating it from a point charge or a very tiny charged particle. Using the laws of electrodynamics. And
well, you're calculating it from an idealized center. They're saying this is the center of the charge. They're not saying this is where all charge exists.
And they also say that charge is the source of the field, not the field the source of the charge.
Right. I would agree that in that sense that mainstream, if that's what they're saying, is that charge is the source of the field, they're incorrect too. It's the other way around.
Yes. But see, we have this problem with when we were developing the laws of the force of inertia, force of gravity, electromagnetic force, we did it in terms of things like charge and mass. And then we discovered that our definitions were not good enough, so we had to invent other theories to supplement them, such as general relativity theory, or in the case here, we had to invent solitons. Well, we didn't actually invent them; we observed them, but we had to do that. And but now that we have better tools, how do we measure a charge? We usually measure it by its fields and what the fields do. And so we discover that we could talk entirely in terms of fields if we talked in terms of structures in the fields like solitons, and we wouldn't have to use the concept of charge. But
yeah. It's like you said. I mean, basically everything is a situation of really being reversed. It's not that the matter or the mass is the source of the gravity. Gravity is the source of the matter, of the mass. Mass does not emanate from, or gravity does not emanate from mass. Mass is derived from patterns of fields, gravitational fields that create the mass, that are focused to mass. So the same is true of electrical. Charge is created by is focused point of energy, electrical energy, not the other way around. Charge is not the source of the electrical energy.
Yeah, but you can also make the force of gravity due to just the vibrations of charged structures.
Yeah, but it's not really. I see it the other way around. The structures are vibrating because the gravity is being focused to that point of that structure, because the structure itself is a vibration of the field. Correct? I mean, there's no distinction between a particle and a field other than the focal point at which it's at.
I would totally disagree with that.
Well, I think that's what Bill's theory is as well, is that the particle is not really anything more than a focused field.
Yeah, and that is a main point of contention. So
yeah,
that's not at all clear which way it is.
And it's good that we can see these differences, and that's one of the benefits of this organization, is that we can see different approaches to try and explain the same data. And the next question is, and this is one of the things I'll be dealing with at the conference, is how do we determine what is true? And so we have two theories that can explain the same data, let's say, And how do we determine which one of them is true? From a mathematics point of view, I could say, well, I could probably invent 1,000 theories that could explain the same data if I don't have very many constraints on my theory.
Well, maybe my paper for the conference will help explain that, because I'm actually trying to figure out how we make those logical deductions, or basically how we solve problems, and how is it that when we say something is true, what is actually going in our head that allows us to do that. And so, my theory is basically starting out that the way we do that is that we set up these sets of logical statements, which are in English, and if basically they all evaluate to be true at the same time, then that's something that we generally believe is true. Versus if we have contradicting statements which are relevant to the subject matter, then those are things that we generally think are false. So I'm trying to just figure out, how do we, given a set of facts, decide whether something is true or false?
Well, unless something fits all the facts, you either have true or truer, but you don't, or true and truer, but you don't have true. You don't have true. I mean, true would have to fit every fact, which means you would have to take every fact into account. But so
yeah,
but it would be interesting to figure out,
we can hope for.
Well, see, everyone is just going to have to come to the conference if they want to learn about that. So there you go. Or debate it.
But that's kind of the theme of our conference, isn't it? Critical thinking, and how do we decide these issues? And don't think it's simple, because it's not. But we can at least see things that are wrong with the politically correct theories of today and approach. But we only have our generation to work with primarily for developing something new, and we may not be as creative as some people have been in the past. I don't know.
See, it says our theme is back to our philosophical roots. See,
Okay.
that's totally going to be about how we decide these logical issues, right?
Right. So, but that's a good thing to talk about, and each of us will be able to hear another point of view at the conference that comes, and we have to try to figure out, how valid is this other approach, what is good or bad about it, and they will be doing the same thing to our approach. And so that's very good critical thinking that's going on. And you don't realize it, but we gain things by talking to other people. Even in my own work, I was presenting at once at a meeting, and a person said, "Oh, you're just following what Isaac Newton said to do." I said, "What?" He said, "Yeah, it's in his book called Mathematical Principles of Natural Philosophy." And I had the book in my library, but I hadn't read it that closely. So I went and looked, and sure enough, I agreed with him. I learned something from him, one of my critics, and I started adopting that. And we all can have experiences like that, and it can improve what we're doing and make it more reasonable to other people, and also make it more general, so that we can describe a greater and greater amount of experimental data that we start with. If I started with thinking I had found the universal law, force law. Well, then I realized, you can't just stay in physics with that. You've got to talk about biology, geology, astronomy. You got all these things you got to explain now if you're going to have a universal force. And so that's a lifetime goal right there. And so I've started on that, but when you realize the implications of what you're saying for your work, you realize many more areas that you need to be able to make sense of, and so that's what we need to do. And I'll be making some attempt to do that in the conference, and covering things on what is life, um, and how does life begin and how does it end, and that kind of thing. And we'll see. There's still some things we don't know, but that we can explain some things. And so that's uh, what one of the goals will be. But whenever you choose an approach that's kind of unique, like Franklin and I have one, and I think some of the rest of you do too, you have many things that you need to explain, and you may have only just considered some, but one day, you'll get to the point where you should be able to explain more, and so that's a goal. And as you start collecting the data and looking at it and trying to see how you could interpret it. And by the way, in quantum mechanics, you have what's called the universal wave function. And the universal wave function has a lot of parallels and symmetries to the electromagnetic field. But in quantum mechanics, it's not a physical thing. But in electrodynamics, it would be considered a physical thing. And so that's, you can see there's a lot of parallels, trying to explain the same data between the different approaches, the quantum approach versus the physical approach, and that kind of thing.
Actually, your mention of these parallels and what is life and quantum mechanics and so on just reminds me that this year, I think it's in September, it will be the 75th anniversary of the presentation of a seminal lecture by Erwin Schrödinger in Dublin with that title, What is Life? In fact, there's a little book which he wrote based on that lecture, which I actually have. Some of you may have it or have seen it. This was pre-DNA time, and it said that he actually sowed the germs of the studies that led later to Crick and Watson's work. I think there's some commemoration or lecture being given in September. I have to look out for that on the thing. But I'd recommend actually, this book, What is Life? One other thing that occurred to me as Bill was speaking, and before that was just mention it, is that, see, the scientific process that we're using in physics is largely synthetic, in that we're applying certain tests and we're applying certain criteria. We're saying, well, look, it must be logical, and it must follow all these steps, and it must comply with all the experimental results. So, but that is really a series of necessary rather than sufficient criteria. I mean, it's necessary that it not be illogical. It's necessary that it not contradict experiment and so on and so forth. But that doesn't prove it to be correct, because we mightn't have applied enough criteria. I mean, I suppose with the synthetic approach, you ultimately have to apply an infinite number of criteria before you can be certain, that you've established a truth. In other words, you can never be certain. You might conceive, I suppose, in the philosophical discussions, it might come up the sort of Leibniz idea that all truths are maybe ultimately analytic. That if you knew enough, you would find that anything that is a particular way could not be otherwise. That it maybe is almost tautological. But anyway, I'd be interested in hearing how those discussions go.
What was the name of the guy that you mentioned?
It's the Nobel Prize winner, Harry, Erwin Schrödinger. Schrödinger's wave equation.
Erwin Schrödinger wrote about life?
Yes, believe it or not. He Schrödinger left his native Austria in 1938. I think he wanted to get out. Actually, it's frequently thought that he was Jewish, but that's not correct. He was Roman Catholic, or he might have. I think he was an atheist later on, but he wasn't Jewish. But he wanted to leave the Nazi regime, and he was looking around for various places to come, and the Prime Minister of Ireland, the Irish Free State at the time, had established the Dublin Institute for Advanced Studies, and he invited Schrödinger, who was a very distinguished man, to come over and be director of that. So he lived in Dublin from maybe 1939 to 1956 or something like that. Now, 75 years ago, you can work that out, whatever that is. 43 or something. In September 1943, he gave this lecture, What is Life? You could actually Google it and you'll just get the information. You could buy the book on Amazon. I have the book. So there's an integration of quantum mechanics and biology. Yeah, there he is. There's Schrödinger. You have it there, Google.
Ian, I'd like to ask this question. I got this book.
Yeah, there's the book. I have that black cover, yes.
Okay, I'm going to talk about another book called this fellow named Hector Houghton. I got this at one of these thrift stores that we have here, and the people donate old books and then they throw them away, and you can just go over to the bin where they throw the books away, and so I got this little book, and it's by Hector Houghton. I've never heard of Hector Houghton, Philosophy for Pleasure, which is kind of a strange thing. But what he does is reviews all the philosophies, the theories of philosophy since the Greeks. And this book was written in 1955. And then towards the end, he concludes, he says that metaphysics is useless, basically. That's kind of what he says. He says the whole what philosophy and everything of philosophy has taught us is that we shouldn't follow metaphysics. We should only base our theories and our philosophical thinking on empiricism or empirical theories. So my question is, do people agree with that idea? That you shouldn't include metaphysics in any kind of ideas or beliefs or thinking?
I don't want to bias anybody in answering that, but when you mentioned Hector Houghton, it sort of rang a bell somewhere in my mind. And I think if it's the same gentleman, he was associated with the British Humanist Association or something like that. I think he might have had some office in that at the time.
I don't know anything about him. Franklin's got the book up there on the screen. I'd never heard of this guy, and so I started reading this book, and he gives a kind of an interesting review of ideas. When he got to the end, I was kind of stunned by what he said at the end, and so that's why I bring that up. Basically, what he was saying. I guess I would summarize this. My take on what he said was that the history of philosophy shows that, in essence, basically, metaphysics should be avoided and discarded. That's kind of my take on it. And I was kind of
metaphysics?
Shocked by that.
What did he mean?
My own quick view is that perhaps most of the ancient philosophy, the metaphysical ancient philosophy, probably should be abandoned. But I wouldn't extrapolate from that all metaphysics should therefore be abandoned. That's just my quick response.
Well, I suggest as a point, there's a website, and I'll just, on Truth and Reality, there's this website, spaceandmotion.com. Okay, you can get www.spaceandmotion.com, space and motion, one word. And he sort of submits that he bases his scientific theory on metaphysics.
What do you mean by metaphysics? I'm still trying to struggle with that.
Well, metaphysics is kind of the primary notion behind this is that there's one reality, and that metaphysics sort of there's a lot of different metaphysics. One metaphysics would be the easiest one to say is that God created everything that there is. That would be a kind of a metaphysics, a type of metaphysics. Religion is supposedly has a type of source in metaphysics. So you can't really prove it by science. It's a principle that you take as true, although there's no empirical basis for it. That would be one way of viewing what that means. But metaphysics in and of itself has a lot of other issues. It deals with
yes, quite so.
Reality, what is existence, what are things that really exist, and traditionally the discussion of time and space, and what is time, what is space, what is matter, that sort of thing has traditionally been discussed as metaphysics.
See, it's frequently thought that meta is like past physics. It's maybe higher than physics or beyond it or something like that. But I think historically it's merely like a classification. It's Aristotle's classification that you have the physics here, and then after that bookshelf you then have the mental, which is past the physics. It's just the next stage of his bookshelf.
Physics. It's after physics, and Aristotle's when they cataloged Aristotle, metaphysics was after the physics part.
Yes, exactly.
But the question sort of boils down to, if you go to this site metaphysics, okay, what he's postulating is that there's a dynamic unity of reality, and so he says there's one, and this has typically been, if you go through the Greek philosophers. Thales said that the universal substance, everything is created from water. Okay. And then I forget, one of the Milesian followers came and he said, no, everything is composed of air. Air is the universal substance. And so now, I would suggest that what Bill said, Bill is saying something like gravity or the field is the universal substance. That would be metaphysics.
Now, the way I came to this and supported it is interesting because Isaac Newton gave some instructions on how to proceed in science to do better. And he said that in each field of science, such as electrodynamics, you discover as many empirical laws as you can. Then you take that set of empirical laws and you combine them together mathematically into a single law. And that is more general than each of the separate empirical laws. And he said, then you compare that with the experiment and see if it can predict more things than the individual empirical laws could do, and see if it can still predict everything that they predicted. And so he thought that was the way to go. So that's the way that I proceeded. So instead of having preconceived notions, I started with the empirical laws, which have some notions underneath of them, like the idea of charge and that sort of thing. But when you solve them simultaneously, you get a solution, and then you see if that solution can explain more data, for instance, the force of gravity, and you see if it can explain what an atom is, what an elementary particle is, what a molecule is, what a nucleus is, that sort of thing. And you just keep trying it out in different fields till you reach the point where it doesn't work. And then it's incomplete. But he said you don't know how it's incomplete until you've tried it in each area. And by using the empirical laws to start with, which are in equation form, you have simplified the process so that it's easier to do. And then after you finish doing that, and let's say you think you found the universal force law, now you can look at questions like what is mass, what is charge, and that sort of thing. And we had some experiments, but no force laws associated with them by people like Winston Bostic that may answer those questions. And so you look and see if they work. And so that's kind of the way that I have proceeded. But so anyway, that Isaac Newton wrote The Mathematical Principles of Natural Philosophy. And it's in that book he tells us how to avoid the pitfalls that people had had in the past by working more with empirical laws. So I've tried to work with the empirical laws for gravity, for instance. We have the quantization of gravity called Bode's law, and I haven't been able to explain that yet. So I'm still working.
But we're coming to the end, Bill. The bottom line is that you just described one version of a method of empiricism, which doesn't really deal with metaphysics, because Newton, was famously said he hypothesis non fingo, so he doesn't really make any hypothesis. He supposedly interrogates nature, and nature guides him to the truth through the empirical method. But I don't, that's just one of the possible methods of empiricism. And then there's other people who advocate, a metaphysical approach.
Yep. Yeah, we are getting towards the end here, so I'm going to go ahead and try and do a summary here. So thanks for everyone for participating. So we started off the discussion with the question of volcanoes and why do they exist? And we went over the conventional explanations that subduction causes these sorts of things, and that's why we see them appearing around these subduction zones, although Hawaii is a bit of an exception, as well as Yellowstone. But we discussed, what are our basic premises about, how did the planet form? Did it form from a ball of gas? What evidence do we have from geology? And does any of this actually make any sense to explain, what's that volcano doing popping up in my backyard, where those poor people have had their houses destroyed? And it seems that, a lot of information may have been ignored and that we really don't have a lot of facts on this whole thing. And a lot of this is probably speculation. So maybe all that heat is coming from radioactive decay, or maybe not. Or, we can speculate all kinds of things, like the core could be some kind of nuclear reactor. And that's what's generating all the heat. So like literally we are sitting on top of a sun-like object. But we also discussed the outer planetary things, like what's going on in Mars and what's going on in the moon. And we probably have even less information about that. But, it seems there are things that are common, like the moon supposedly also has a molten core as well, but no volcanoes. But we did do a lot of discussions on the philosophy of science. And that is kind of the theme of our conference. That why is it that mainstream ignores stuff? It may not be deliberate, could be out of laziness, could be that I think that 99% of everybody is a sheep. They call them sheeple, right? So if you have a bunch of sheeple, then maybe that's what we see in the mainstream is exactly what we get. But there were some books presented for anyone who would be interested. The Philosophy for Pleasure by Hector Houghton, and it appears that most of it is actually readable on Amazon. And from Erwin Schrödinger, a surprising book about what is life. And we also discussed a little bit about how Newton seemed to have the right ideas, or that maybe metaphysics maybe not such a great idea. But that was all great discussion today. And that will do it for today's episode of the Science Chat. And please watch out for the announcements. Probably I will be busy next Saturday, so we will probably not have a Science Chat. So just continue to watch for the announcements.
Thank you.